different version of the lecture format for the video, and we did a joint conversation talking about horror stories related to working with big networks. And so what we would like to do now is share a little bit of that with you, and I'm just going to really briefly just point out our main rubric for thinking about analyzing big networks and the multiple ways in which networks are big. And then we're going to do what we didn't do in the presentation, which is John's going to just do a walkthrough of a couple of the strategies with a real live data set. So just quickly to set the stage for those that didn't have a chance to see the presentation, I cut my networks and health teeth on Ad Health, and this is just a quick image of the number of nodes and the number of edges in all the Ad Health schools. And so if you're going to go through, there are a couple of networks that have a couple thousand nodes in them, and you have most 10,000 edges, right? So this is the scale of the size of networks in Ad Health. And this is what you can get in without like a moment's thought going to networkrepository.com and downloading some social graphs. We're talking on the order of 250 million edges, right? And so the entire Ad Health corpus, right, fits down over here. And the scale of networks that we have to deal with is just so much larger than it is in those kinds of face-to-face survey-based collection strategies that we've kind of gotten used to. And I think that this is a bigger problem because the intuition and the tools and all of this that was built in social network analysis, from the 50s and 60s forward, was built around a small case study rubric. That was the logic of how these tools were developed. And it made sense to go ahead and do things like focus on geodesics and betweenness that were relatively easy to calculate. They were straightforward, and you only had 30 nodes in the network anyway, so it didn't really matter. So we went with that set. Real life networks, again, I said now, especially today with lost online networks or other sorts of really large bipartite networks, are just so much bigger. And so we want to think about ways to deal with that. And so there are a couple of classic problems that pop up when you think about big networks. And one of them in particular is, particularly with bipartite or other kinds of text networks, is that the relationships in theory are all-to-all relations and differ in their quantity, not in their presence or absence. So every document in the world shares a subset of simple verbs and adverbs, right? So those documents, those links are there. That doesn't really mean they're similar to each other. In fact, they're kind of boringly similar. And so thinking about, there's a bunch of really interesting and important questions you have to think about for big networks that have to do with thinning or backbone in the network. And I talked about this briefly yesterday in one of the sessions, and I forget which one, that we sort of think of there as being three basic ways in which this happens. You can either come up with line models, you can threshold something, you can rank edges around nodes, or you can have some kind of a model for whether a tie is greater than you'd expect by chance. We also like to think of it in terms of essentially three ways in which networks can be big. So you have the classic idea of a big network, which is a lot of nodes and a lot of edges. And then you want to ask yourself, what kind of questions are relevant to be asked here? Because it turns out that many of the things that we think of as methods problems are really just theory problems masquerading as methods problems. And what we want to do is say, let's go out and run betweenness centrality on my billion node network. But that's just bad theory, because betweenness centrality doesn't make any substantive sense across a billion nodes. But other kinds of centralities might. So you want to think very carefully about what is the social process of interest, because that's going to narrow the scope that you work with. The big networks are the ones you might imagine, right? The other sort of kinds of networks we think about are what we're calling deep networks. And deep networks are networks that might be on a small number of people, like kids in a Data Plus program. But then you might have 30 terabytes of video data that you need to parse in order to get something interesting out of that. So there's a really focus on the details as opposed to the macro structure. And then the other thing that happens is a lot of the times now we end up with lots of repetitions of our networks. So we get many replicates of the same underlying data generating process in some different settings. These can be friendships in villages. These can be kinship networks across counties. They can be bipartite networks of purchasers and products in different stores. But essentially you get the same network in many instances, and you need ways to move away from our intuition-based models of case study work to something that you can routinize across perhaps 1,000 replicates of the same thing. And so that's the way we like to think about this problem: is big networks, deep networks, and many networks. And the basic solutions that we proposed in this project is that for big networks, the main solution is to divide and conquer. You have to find some way to break your network up and then work on the smaller pieces. And the two ways to do that are either to follow the natural fissions, which is to take a community detection approach, or to localize and to focus on some neighborhood around a sample of nodes. For deep networks, the problem is you just have too much information on each case, and most of it can't be relevant. So you have to aggregate and filter in some interesting ways. And then if you have many networks, the real challenge there is usually not doing an analysis on any single slice of those many networks, but it's doing something consistent across all the slices. And mainly what that requires you to do is to think about what the ways in which you make choices for something like block modeling or resolution parameters or something, and then regularizing that. And so it's really is just an exercise in rigor on your own part to move from intuition to practice. So that's a big picture of what we see in big networks and big problems. And now I'm going to turn it over to John, who's going to give a demonstration of how we use some of these big networks. So okay, I'm going to stop my share.
Yay. All right. Sure. Okay. People see my screen?
Yes.
All right. So for people who want to follow along on the demonstration, I suggest putting there was a zip file, SNH BigNets. I suggest putting that file on your desktop because all the paths for the demonstration are routed to your desktop and you don't have to change any directories in it. Okay. Hitting the script in the chat, I put in this install script. So this will install all the packages you need for the demonstration, with one exception, which is this word cloud piece. You just run these two statements: require dev tools, install, you'll get word cloud. That's for the last little part of the demo. And for those of you, which is probably most of you, who don't have web shop just in as a package, you may be asked, hey, you don't have Phantom.js. If you run this script, which is also in the script, you'll get it. Okay, so that's the logistic details piece here. So let me just, well, I want that back, but okay, so I'm just gonna get my package set up, and then I want to talk a little substantively about this network before we dive in. Not too much, but just running this, getting this stuff set up. All right. So what are we analyzing? Well, we're analyzing this fun little data set. It's actually on the Payek, which is another software analysis package. Actually, let's say hi to Payek for a second, just notionally. Payek is one theme in this is that there isn't one social network analysis package to rule them all. Payek is another nice one. It's also quite effective for large networks. And we may talk, depending on how much time we have, about how to use it, or people can talk to me about offline. So the people that make Payek, they have this nice Marvel data set. This is the original graph, which is in your folder, is a bipartite graph between characters and comic books. And it spans from 1961 until the early 1990s. And when you think about Marvel Universe, and I could give you a substantive why would we analyze Marvel. I'm just going to tell you that I like it because it's fun and it was a cool thing to do a demonstration on. But there's two important things about Marvel when we think about it as a graph. One of it is actually a universe. So there is a potential for all characters to be connected to all other characters in Marvel. And because anything can happen in Marvel, it has happened, not always well. But fortunately for us, the likelihood of that actually happening is not, for any one pair to co-occur, is not equally likely. So we don't actually get a spaghetti string network when we look at this. And I'm just going to quickly go through a couple of reasons why, which will help make sense of why we're doing the things we're doing in the demonstration. So Marvel, unlike DC Comics, started with teams. And the first Marvel universe was Fantastic Four. And the reason why that matters from a network's perspective is it's easier to grow the Marvel universe than, say, DC Comics. And the reason why is that you can introduce a new character if, say, Spider-Man, well, that's it, as just part of the adventures of the Fantastic Four. That's how Spider-Man got introduced. And if you don't like Spider-Man, then it's a minimal investment. DC just doesn't continue the series, and it's okay. But unlike in DC Comics, where you have Superman or Batman, these super high-powered heroes, if you introduce a character, that's really quite a big deal, because Superman is just not going to care about someone who is not really powerful. And so it's actually more of an investment for DC to add a character. So Marvel can actually spread fat quickly, but fortunately for us, Marvel characters, there's sort of three kinds of comic books that they appear in a lot. There's these teams. There's serials about the comic. So Spider-Man, even though he's introduced as connected to the Fantastic Four for like a second, he generally appears in his own comic book, or comic books that are sort of offshoots of that comic book. He doesn't appear in tons and tons of team-based comic books, even though occasionally he collaborates with somebody, fortunately for us. But the Iron Cage, Marvel is not immune to it either. Basically, what happens from a storytelling point of view is that the characters that face bigger challenges. So you can't, basically, it stretches plausibility that a universal challenge is going to be managed by one character or even a team of characters. So they create corporations or firms or whatever, S.H.I.E.L.D. in this case. So we have three kinds of comic books, which, remember, that is a bipartite graph originally. So it's characters of comic books. The characters are more likely to appear in. And there's one other factor that is a homophily effect on this network that keeps it from being a spaghetti network. And that is that there's a connection, depending on the particular Marvel comic book, there's a connection between the powers and the major issues that the comic book is trying to address. So in Marvel, the main source of powers is genetic variation. The main themes are, what is the role of science? Will science lead us to become better people, which is the perspective of Professor Xavier? Or will science actually just amplify our negative tendencies, and we have to look out for that? And that's the perspective of Magneto. So to the extent to which the power and the themes are connected, X-Men is not going to co-occur with Thor. Thor is magical, or he's so scientific that it just pushes understanding. So with that said, we can now return back to the Marvel Universe. Now we understand a little bit more about this graph. All right, these first steps, I'm just loading some functions that I use. It's not a huge thing. And I'm going to pull in my network. And just as a reminder, this is our node list, and these are our ties. This particular network is actually the one-mode projection of that bipart network. So this network is characters connected to other characters through shared graphs. So you could do the full set if you wanted to. Now I have this little function where I'm generating an iGraph because I'm going to do some partitioning, and iGraph is nice for that. I'm going to do Louvain partitioning. I'm not going to go in big detail, but the major things here is, for an iGraph object, I've got to move this to 0 index. And then I've got statements in here that you guys can copy to move this nodes and ties into a network object. So I'm just going to, and for navigating the script, you can just fold up the function, or you can fold up the entire section to make it more navigable, because I know there's a lot here. All right, so let's just make sure, oh, that's too much. All right, let's just make sure that things look okay. So I'm just going to look at the top. This number of vertices matches the number of vertices I found in the pulled in object, so life is all right. So we're going to come down. Well, let's just check there's some edges. I don't want to be too sloppy here. And if we look at the top, the ties match the ties. So life is okay. So we have our object. But I mean, lonely isolates, sad pendants, they're important, but not today. Because what I'm really interested in is sort of the central organizing principles behind the Marvel universe. With all these different comic book types, what's really going on there? Like, is X-Men in the center, or is it Spider-Man? What's up? So I'm going to first get the largest component. So how I do that is I'm running this running clusters MarvelNet that says iGraph. MarvelNet is the iGraph object that we created. And then I'm just saying, hey, I want the largest one, which is what this which max component C size is doing. And if I run these three statements, I'm going to get this new graph called Marvel LC, which is this Marvel largest component. And the person doing that is often with these super large networks to begin zooming in on stuff. You may want to, the largest component's a nice place to start to again feeling around what's going on, right? And let's just check that that worked in that we have fewer, not a ton less, fortunately, but fewer vertices than we had in our original set, right? So about 40 less vertices. Now here begins the magic in the sauce. Peter's going to go a lot more detail, a lot more rigorously on Louvain clustering, but I'm going to identify some Louvain clusters. What's the purpose of this? I'm going to take this top-down view, and I want to identify the community structure to get a general sense. And then for today's demonstration, I'm going to focus in on a community. And I'm going to use the intuitions from the graph right now to focus in on what community. Now, there might be other times you're like, I already know what community I want to focus in on. But it's just sort of right now I want to get a sense of what's interesting topologically. So I ran my Louvain communities. And why else am I doing this? Well, I don't think it's sensible of running a measure on this entire graph, given all the homophily dynamics I just described. So I'm using this community detection to help identify subdomains in the graph that might have their own internal organization, which is meaningful. Okay, so that's another reason why I'm not just running degree or something on the entire graph, is I have a substantive reason, domain-specific reason about why I'm doing what I'm doing. So I'm doing this little shrink network function. I'm basically doing this so the code's a little bit readable, but the iGraph arguments are in here. And basically what I'm doing is I'm going, hey, I want the communities to be, the number of people to be the number of communities, and the number of edges to be an edge between communities weighted by how many people are between each community. So I'm going to shrink this, and we're going to look at just how many we get. And we're going to visualize it in a moment also to get a sense. So on this first wave community detection, I would not, by the way, treat this as the holy gospel, but as a first bit, we see that we're getting 28 communities. And I'm going to calculate the community degree so that I get a sense of the level of connectedness between these different communities. I'm just changing the directory paths because I want to output some figures. Okay, so you might see this and be like, well, that's kind of weird. Why am I doing that? I'm just making an external plot window because I want the plot to have it look like the way I want it to look. And if I have it down here in the plot window in the corner, that depends on the size. So the figure I want will actually look like this because the dimensions are predefined. So let's look at this community structure. Let's pull up my plot. All right, so now we have this nice, we took this really large network, well, and we reduced it once with this one mode projection. And there's a community that sort of just strikes out at me as being interesting, which is, well, all of these are interesting because I'm a Marvel fan, but community 10 looks particularly kind of fun because it looks highly connected, but it also looks like it's connecting these pendants in a kind of interesting way. So I'm going to focus in on community 10 for today. Actually, I would like to leave some time to make sure that we talk about what choices might have been better choices than the one I'm making. I'm not saying that this is the definitive way. I want you to get a sense that you're going to go back and forth on this analysis. Also, why do I have this degree plot underneath here? Well, I mean, the community plot gives me a general sense, but maybe I want to sort of know the magnitude of the differences. What's sort of nice is I know that this graph, which 10 and 26 are the most connected nodes, they're connected in a sense of, 35 to like 1, right? So I have a sort of general sense of the scale of these effects, and I can see the two groupings between a bunch of nodes that basically have one connection and a group of nodes that's much more highly connected. I'm not going to output my plot, but you have them, and you could do this. So now we're going to focus in on community 10, and we're going to look at its particular graph. So I'm just doing the same trick again, where this is the iGraph membership. But now I'm doing this on Marvel largest component. And I'm going to pull out community 10 specifically. So I zoomed out and now I'm zooming back in, okay? So now we'll look at community 10. Just look at the number of nodes quickly. That's about a third or so of the original set, or 6, sorry, not a third. And now I'm going to pull out the graph of that community here. So this is, oh, sorry, I've done that. Let me just rerun these and make sure I did that. Yeah, I did that because I have the diversity. So now I'm just calculating the degree to give myself a sense of, well, maybe there's sort of important people within this community. Let me get a sense about that. So just doing that. And I'm going to do a subclustering. We talk about this in discussion of doing first or second level clustering. In this case, I'm doing it because I think that was a fairly large graph. And I think there might be actually even relevant subdomains within even that community graph. So I'm just going to do a second level clustering here. We can talk about what sort of diagnostic reasons you might want to do that. Like, for instance, if that community graph earlier had nodes of really different sizes, we might want to do a second level clustering simply because the communities aren't even at the same order of effect. So I'm going to pull that out. And I'm just going to quickly, I'm doing the memberships, and I want to draw this new graph, give us a sense of what community 10 looks like. This takes a second because I'm basically iterating. The poor thing is working very hard it's still a large graph, to get this layout to be at all attractive. It's also iterating pretty hard to get a relatively decent solution, cluster solution for me. So this takes a second or two, but it won't be forever, I promise. And you could cheat, you could look at the image already. Don't do that because it's my only sort of my magic trick here is I get to show you these images. This is part of the thrill of life. But we could think a little bit about, hey, I want to emphasize that we're going to do this back and forth. I'm only showing you sort of a first level thing, but here we've got community 10. And now let me pull up the thing again. And cool, all right. So we have this large community, but at least it's not so huge that I can't even visualize it. And I'm getting some interesting subclusters in it. And so, okay, there might be something here, but it's still a very high level visual. So I want to look at the third piece, and I want to get a sense of, well, who's in here? Who are these sort of sub-teams? And I'm going to focus on, let me explain this graph a little bit. So these are sized by degree. These are sized by size. So I'm going to focus on 6 and 9 because they seem particularly prominent. They have both a high degree and a large size. And I'm going to pull these out. And I'm doing some word cloud magic. We can talk about offline if you want. But so basically what I'm trying to do, and this is a part of this, is you're going to have to look at your data at some point, especially with such large data, to like get a sense of, all right, well, okay, I see some communities. Do they make any sense at all? Here, these are sized in relation to degree, and I'm trying to capture the majority of the objects, and I have not specified a particular layout. So, and what we're getting to see is, well, they look like X-Men. Actually, they kind of look like X-Men villain characters, and let's look at the second one. I'm just pulling these out to get, oh, okay, I can kind of see some differences between them. But why not we look at it as a whole and compare them and see if we see anything? Because partially it's also because I have to admit I have my R thing so zoomed out that it's a little bit difficult to look at. Let's see if pull this out. And here's a sort of final graph. All right, so we definitely have the X-Men. And it's not surprising that they were kind of out doing their own thing, because remember I talked about that they have their own they have a pretty strong aesthetic, and comic book fans really hate the violation of the authenticity of their team. Like they punish with the comic book makers if they violate this. And we talked in the talk about community and degree and how you could use this. So we could, if I had, this is sort of the beginning walking points of what would be a positional analysis potentially. But the main thing here is on these low degree nodes, most of the low degree nodes have some connection to somewhere else. So this isn't an extremely insular community. If the black and the brown degree lines are really close together, that would say this community is not only like a clear community, but they basically, the ones that are not well connected, they're really just insiders within their own community. X-Men is such a powerful team that frankly, even the low degree nodes have some connection to someone else. And the second part of the code is just showing how you could do this in Payek. I think we're sort of out of time to do that, but I would, if people are interested in how to work with Payek, why you'd work with Payek, I'd love to talk about that. We could talk about that like offline or in a workshop or in one of these sub rooms or something like that. But this is, I think I'm going to turn it back to Jim and allow for sort of more general questions, since I realize this is quite a speedy demonstration. So let me stop sharing.
Okay, great. Thanks a lot, John. So, it's always, that was a great, and if you get a chance to go through and look at John's script, which is posted on the piece, it's a nice exemplar of the ways in which these tools can be used. The big picture sort of summary of all the big, if your problem is your network's too big, the solution is you got to make it smaller. I mean, and the question is, how do you make it smaller in a smart way? And it turns out that that's often question dependent. And so I think I'll just, so that's sort of the first big point. The second big point is that oftentimes the problem is not a network problem. Many times, like, and John and I have worked on graphs with 40 million nodes on other projects. And these kinds of things, the problem is rarely getting iGraph to do what it needs to do. The problem is getting the data off of some JSON file into R or into whatever package you're using. And so there's a huge amount of investment that goes in with these things. It goes into essentially database management. So again, we're happy to talk offline or to help you with a project if you have a big one. But the series of strategies for that tend not to be network problems. They tend to be database problems. With that said, we are running a little late, but I do want to open it up. Are there questions or thoughts or ideas that people have had or reactions to this? Is this stupid or silly or like what's going on? Please, Gabriel.
Hi, I hope the mic works. My camera sure doesn't work. So I'm going to reboot and hopefully work. I had a question about, you quickly went over it, and for the sake of the demonstration, it made sense to do it substantively. But you talked a little bit about how you would determine how far you iterate on the clustering angle of things. So like what's the level of depth you would want to go to? And so other than just a substantive reason, you kind of highlighted maybe that there's like a programmatic way of doing that as well. And if there is, I'd love to hear a little bit about it.
You could do a resolution. Actually, this is going to be Peter's bag in the next talk, but you could do a resolution analysis where you essentially, you wouldn't do this on the super largest graph, but on this, once you have their first clustering, if you found clusters that you thought were particularly interesting, you could then begin comparing what is the community solutions at different resolution parameters. And iGraph now finally supports that. So there's a whole methodology. Peter has a really nice paper. It's called CHAMPS. I like the acronym. He goes for good acronyms. So it's easy to remember, and that walks down through actually a methodology to think about comparing community solutions. There's some other pieces we could talk about also, Gabe, if you want to.
I would just echo that that for these multi-layer, the point that I think Gabe is pointing out is that one of our solutions to the divide and conquer is that if it's too big when you start, you cut it in half, you can keep nesting this as long as you want, arguably. And the question is like, what's your stopping rule? And I think that what you just said was, what's your stopping rule, sans substance? And I think the answer is nothing. So it has to be a substantive rule. And at some point, my general rule when I've done this for big sort of production processes is I will go through substantively, and I will look at and do a second level split of a cluster into subclusters. I will go and look at like what resolution parameter, what modularity value is giving me for that cluster a substantively different set. And then I will do that by picking and choosing, I'll literally look at I by 20 or 30 of them, and then I'll apply whatever that resolution rule is to the other 200. And so, or that modularity rule is to the others. So it's ad hoc in that sense, but it's ad hoc defined by going through it again.
One other quick thing,
that makes sense.
When you're doing a thinning step, determining if you're thinning correctly is also similar. So you'll thin the ties, and then you'll look at, well, is the thing that it says is similar, is it actually similar or not? So you have to do that not just at the community stage, you actually have to do it even earlier at the thinning stage as well.
All right, so we've already stolen way too much time for Peter. Show of hands, do people need a break, or could we steal from the break and just go straight into Peter's work?
We do have one last minute question.
Okay.
It says here, question about deep networks. I recently worked on an event data set which codes time dimensions, so year, month, and date, actor level information, and location information for each event. There's also information about which events are derived from or results in which events over time, so like the from ID to ID. I'd like to explore the causal relationship, or at least association, among these events, change in structural effect, and evolution of event network across space over time. What would be the appropriate method for answering this kind of question? Looked at a hierarchical network, but don't see a method that tackles both space and time dynamics in networks. Maybe this is a more general question.
Yeah, this is a good question. My intuition is this is a relational events model question, if I'm understanding it right. But the question sort of turns on whether or not we're building the network from. We want to analyze the network sort of in a textual network sense, that one event leads to another event, or do we want to model the emergence events as a function of the people that overlap on them? If it's the latter, that ends up being a relational events model question. Let's ping this one to after the lunch break, because I think it will be a little bit more telling when we see what the Sienna models and those kind of models do for that. All right, Peter, I think I'm going to say that if you need a break, take it, but the rest of us won't. So, Peter, we're going to fire.